Hi everyone, today we have Pri3D. Can 3D priors help 2D representation learning? Let's go.
Yeah, thank you for having me here. So basically, I'm Jiho, currently a research scientist in Beta Labs. And previously, I had my PhD in Technical University of Munich with Matthias. So my focus is on the 3D scene understanding, something about 3D representation learning. That's about it. So today I'm gonna present this paper from last year SCCV. So it's called Pri3D. Can 3D priors help 2D representation learning? So this paper is basically talking about how can we better leverage 3D priors for training some 2D backbones. So I think I just started. Okay, so the idea in this paper is quite straightforward. So basically, we introduce two different losses that for pre-training that can embed the 3D prior into the 2D backbone. The first one we call it, I'm not sure it's okay. The first one we call it let me do it another way. I don't know why it plays automatically, but I think I think
no problem.
Okay, so the first one is called a view-invariant contrastive loss, where we try to leverage the multi-view information to have some 3D priors for pre-training. Another one we call the geometric prior contrastive loss, where we try to do the contrastive loss between the pixel and the voxels. In this way, try to embed some geometric priors. So, and after the pre-training, we wanna fine-tuning on majorly the scene understanding task, such as the semantic segmentation, object detection, and the instance segmentation. All this, popular scene understanding task. And the motivation is that we now have seen a lot of challenging works or benchmarks on the real world RGB data, for example, ScanNet, and also the other benchmarks. And now we think we have so many RGB-D data, and can we do something like unsupervised pre-training to get better representations for the scene understanding task? Normally, people would think first, can we do something to improve the 3D task? But in this way, in this work, we try to explore, can we improve the 2D downstream task by using the 3D priors? So we basically take the RGB-D data from ScanNet, and we use our pre-training method. Then we fine-tune a downstream task on the ScanNet 2D benchmark. So the rough idea is also very simple. So here, we first introduce our first loss called a view-invariant loss, because on the RGB-D data, it's normally a sequence, it's a video, so that in the video, you can find the overlap of different frames. And in those frames, you can actually find the correspondences of two frames, so that you can leverage the multi-view information from this data. For example, in this image, in the ScanNet, there are two frames. They have some overlapping regions. Then you can find their correspondences between two frames by their camera poses, etc. Another loss we introduced called the 2D 3D color geometry correspondences, which is we try to contrastive loss between the point or the voxels in 3D and the pixels in 2D. So basically, they should be same thing, but just in two different modalities. One's in the RGB space, one's in the geometry space. So to achieve this goal, we first basically introduce our method. The first one is for the view-invariant contrastive loss. So basically, you have two frames taken from two locations in the scene, and they must have some overlap. So we have to pre-process the data. Otherwise, you cannot really do the contrastive learning based on the multi-view information. So the idea is we use a shared 2D backbone. Here is basically a ResNet. And then to process these 2D images, it's actually a ResNet UNet, so that you go back to the original resolution in the output. And then because you know the correspondences between two frames, because you know the camera pose, etc., you can project them. And then you compute the so-called view-invariant contrastive loss between the correspondences. In this way, the two pixels that they are looking at the same location, their features will be pulled together. And if they're not from, if they don't look like, if they don't look at the same location, their features will be pushed far away. And the idea is that they are actually consistent in the geometry. It's only because they're different in the pixel, in the color, because the lightening or view invariance, whatever, but they're supposed to be the same in the geometry. That's why we try to embed the 3D geometry priors onto this the color backbones in this way. Another one is we call the geometric prior contrastive loss. In this way, it's more direct. It's not really we use the multi-view information to embed 3D priors. We directly embed 3D priors between the pixel and the voxels. So what we do is we still use a 2D backbone to process the color images and go back to the original resolution. So you got this feature map at the same that has the same input size as the input RGB color image. And again, we introduce another 3D backbone. Here we use the sparse con, which is the most powerful backbone recently, or currently, or last year, still powerful. And then we use this backbone to process the point cloud, and then we get the feature vectors per points. And then because we know the corresponding relations, because we know the reconstruction and intrinsic, the extrinsic, etc., then you can project the color onto the point. Basically, you know the correspondences between the pixel and the voxel or points, and then you do the contrastive loss again. So basically, if the pixel and the points are the same thing, actually, their feature will be put together, and if they're not, they will be pushed far away. In this way, we can embed the 3D geometric priors to the 2D backbone.
So, right, we have pixel representations in like some latent pixel representation vectors. We have some latent voxel representation vectors, and you also have the correspondence between pixels and voxels from your classical algorithm that matches up pixels with voxels, or you can generate the image from 3D information as well. And then you say, yeah, these representations that where the pixels correspond to the voxels, they should be similar, and otherwise they should be dissimilar, right?
Yeah, exactly. This is actually, if you think it through, is similar to previous laws. So for the view invariant loss, what you do is for the pixel that because of the lightening of view invariance, you have kind of different colors, but they're actually the same points in the 3D, in the geometry. For example, if you look at the corner of the bed, they're the same, but because of your camera in different views or lightening, they appear a bit different in the color space. Yeah, that's for the view invariant. But in this point, it's actually something similar. For example, if you look at this view, the feature of for example, the bed corner are pulled close to a point on the geometry, on the point cloud. They are pulled together. But imagine there's another view come. Look at the same, the corner of the bed. And then for the other view, the feature of that corner of bed will be pulled together again. So in this way, you actually pull the feature of the pixel, for example, the corner of this bed, together again. So basically, you use the point representation as an anchor, and to pull the feature together for different views.
Yeah. Okay, and in the chat we have the question, how do you obtain the correspondence between pixel and voxel?
Yeah, so basically we leverage the reconstruction process. When you do a 3D reconstruction, you actually have the RGB-D frame, right? And you have the camera pose. Then you can use so-called volumetric fusion, etc., to fuse a 3D point cloud. And during this process, you already know the correspondences between the pixel and the voxel. Basically, you first back project the pixel location into the camera space according to intrinsics and depth, and then you use the back.
Can I give it a go? So we have our 3D volume stuff, and then we just render a 2D image from it, right? And from this rendering, we already have the correspondence between pixels and 3D.
You can imagine like this. It's the same principle. The only difference here is we didn't use a rendered color image. We use the actual color image when you record the video. Well, you can also render a new image based on a camera pose and find the correspondence. But in this work, we actually use the real image.
So the way that the 3D stuff is constructed is by having multiple images, and then we know the locations of these images, or where the camera was when we took these images, and we have the depth of each pixel also associated with the with the pixel and not only the color. And then from these images and the camera locations, we can solve some linear systems of equations and end up with the 3D representations, or the 3D volumes. And from this reconstruction, or this 3D 3D reconstruction process, we already have the correspondence.
Yeah.
Okay.
Exactly. Yeah, we I think so. This yeah, the image is obtained with. I mean, I think it's like a reading group. We can just chat during the presentation if you have any questions.
Yeah.
So the image is obtained with a view angle. Yeah, the image is obtained with not only the view angle, but also the translation, rotation, etc. Those camera pose information. 3D point can generate the same image using this. Exactly, you can generate the same image. Well, the same means the content will be the same, but the color style could be different because you have some different rendering, like, you know, shader, etc. Then you could have different style of images. The color could be different, but the content is exactly the same if you have the same camera pose. Yeah. Okay, then yeah, this is for the loss here. So the idea, the core idea is basically for the different for the same location, although they have different appearance of the pixels, their feature space should be pulled together. That's the core idea of these two losses. And then we also try just combine them, right? Because we have two losses, we can also train them together. So here we just try to combine these two losses together, and with the 1-to-1 ratio, basically they have the same weight in the loss computation. And then we use this pre-trained network. If you go back, so we have this shared 2D backbone and a 3D backbone. So in our downstream task, because we care more about the 2D downstream task, then we basically remove the 3D backbone and only use the 2D shared backbone to do our downstream task. So the first one we do is semantic segmentation. So basically we observe with our pre-training method, you can achieve basically better semantic segmentation on the scene understanding task. For example, our baseline could be the ImageNet pre-trained model, where you just pre-training on the ImageNet. And then with additionally our pre-training method, we can get more clean semantic segmentation, or you can see is more multi-view consistent semantic segmentation. So basically, we leverage those the multi-view or geometric prior to have better representations for 2D downstream tasks. Here is some visualizations, and then go to the quantitative results. So basically, we have some baseline. First one is training, like without any pre-training, you just take a random initialization. We call it scratch. So basically, you have the worst performance. The mean LU is the lowest, and then we have the ImageNet pre-training method, where you leverage the 2D information like the ImageNet as pre-training. Then you got way better performance. So basically, the pre-training is very important for 2D task. And then here comes our method. Basically, a view means if you only use a view-invariant contrastive loss. The geo means if you only use the geometric priors, the contrastive loss. And the view plus geo means you use both loss training together. And here are some baselines in between. For example, this Moco V2 series baseline. So basically, for those one is we first use a Moco V2 pre-trained weights, and then pre-train again on the ScanNet, because we want to know how much gain we have by using more data, because we use additional ScanNet data more than only ImageNet data. And we want to know how much we get from the loss itself, the multi-view information. That's why we have those baselines. And also we have something like the depth prediction. Basically, we use depth prediction as a pre-training method, where we use kind of some depth priors, but not totally the multi-view priors. So we can observe the consistent improvement by using this multi-view geometry loss to have better representation learning for 2D task. So then we also verified on the other benchmark. It's called NYU. It's still an indoor data set, but different data set from ScanNet. So basically, pre-training on ScanNet, but fine-tuning on NYU. We want to see if it can be transferable, at least in the indoor scene data. So we also observe some similar trend in the indoor scene data. We can also observe the gap here. And then we verified on different tasks. For example, not only on the semantic segmentation, but also on the instant segmentation, as well as 2D detection on both ScanNet and NYU. So we all observe the consistent improvement. Compared to our baselines, such as training from scratch or use ImageNet or use Moco V2 pre-training on ImageNet, then again pre-train on ScanNet, etc. Well, the only thing that could be noticed here is that sometimes the view plus the geometry get the best performance. Sometimes, occasionally, use only geometry get the better performance. Where we assume it's because if you do the contrastive loss between the points and the color space, it's more stable than the multi-view information. Well, in the implementation, there are some thing that could lead to variance. For example, when you get the correspondences between the pixel and point, it's not exactly one-to-one because there will be some small errors. So we have the threshold, let's say 2 centimeters. If the pixel will back project into the point cloud, if the closer point cloud is within 2 centimeters sphere, we consider it as matched, something like this one. And similarly for the multi-view information, when you project the pixel on another frames, you use the, let's say, the nearest neighbor search to find close the pixel correspondences, etc. This is one thing could lead to this small variance. Another thing could be just this geometric prior loss is more stable when you directly do the contrastive loss between the pixel and the points, rather than you use, project into another frame. Yeah. So we want to see also if our loss, the pre-training loss we propose, is agnostic to different backbones. Then we do on different SOTA backbones. For example, the DeepLab v3 and DeepLab v3 Plus and PSBNet. Those backbones are all state-of-the-art C understanding 2D backbones. And again, we compare our method with our baseline, basically the ImageNet pre-trained. We can see the constant improvement on the 2D semantic segmentation task on the ResNet 50 backbone. And then another thing we really care is about the so-called the data efficient learning. So what we do is so because in the pre-training, you don't have really, you don't really have any supervision. You don't need the label. You don't need the human effort. You just need the camera pose and depth maps. Those are automatically generated by the hardware. You don't need any human effort. But in the downstream task, when we fine tuning, for example, the semantic segmentation or instant segmentation, you need the human labeling. That's quite a lot of effort. So that's why we research on this so-called data efficient learning. Imagine you only have 20% annotated data, how much performance you can get as if you have the 100% annotated data. So in this way, we compare with the baseline. One is ImageNet pre-trained again. Another is the Mocha V2 pre-trained on ImageNet and pre-trained again on ScanNet. So we observe a constant gap across different percentage of training images. For example, 20% training image available with their annotation, 40% into 100%. So the gap will become smaller when you have more data, because it's I think it's observed already that if you have infinite amount of data for fine-tuning your downstream task, you don't even need the pre-training. But the key point is that we don't have infinite amount annotated data. And so one observation is here, with less than 40% annotated data, we can already achieve the similar performance as if you have 100% annotated data, but you use the ImageNet pre-trained model. It's quite impressive, so that we can save a lot of human labeling effort in the downstream task. And then we show some visualizations here. Here is basically, if you imagine what the network is doing in the pre-training, is basically learn the multi-view information or the correspondences between the multi-views or the geometry or the frames. So then we visualize if in the pre-training, if we really learn what we want to learn. So basically, so the visualization here is basically we show what the pre-training is doing. So you can see it's quite impressive. They learn really good correspondences actually. For example, if you saw these correspondences between the far view and the close view, like those chair, or even with very large view variance. For example, this desk here, you can see it's very large view angles change. And also sometimes you can even learn the correspondence on the white color or plain surface, which is actually very hard, because in the color space, if you look at the wet plane, it's basically all wet. There's no different colors in the neighborhood. But if you have some geometry priors, you could learn those correspondences way easier. Yeah, then another question we really interested in is about the transfer learning, because we showed if we pre-training on ScanNet, but the fine-tuning on NYU, we can see the gain also, but that's also indoor data set. It's a basically very similar domain. Now we want to see what if we do pre-training on outdoor data, how it really looks like, rather than only indoor data. So what we do is we pre-training on KT data. You can see here again, because in KT data, we also have the point cloud, we also have the camera pose. We can again find the correspondences between frames. For example, here, you can find this correspondences on the streets. And then we do the pre-training and we fine tune on the cityscape. Cityscape is a pure 2D data benchmark where you do the semantic segmentation, etc., but only with 2D images. Also, another thing we try is we pre-training on mega depth. The mega depth is collected something like data, but use CoMap to reconstruct their camera pose and point cloud. It's a kind of sparse point cloud compared to the sensor depth, but you can still find some correspondence, but it's sparse between different views. For example, on this building, you can find it, although they have different shining effect or the lightning effect, but you can still find the correspondences. And then we show the performance. So here, so the first one, like what do we do? Like this color, the 1, 2, 3, the third row is we pre-training on the for example, if we pre-training on KT, but the fine-tuning on the cityscape, we can achieve 56.3 compared to ImageNet pre-train, we have something like 2-point improvement. And also, if you're pre-training on the mega depths and the fine-tuning on cityscape, you can also cityscapes, you can also observe something like 1-point improvement. I mean, the gap would be bigger if you do it on the KT. If you're pre-training on KT and fine-tuning on KT, is basically same data. Then you have larger gap. And if you're pre-training on mega depth, but fine-tuning on KT, you have smaller gap, but still better than only ImageNet pre-trained model. So in this way, we try to verify how it looks in the outdoor data in this way. And another thing is we really tried that we just pre-training on ScanNet and fine-tuning on COCO, because COCO is quite a challenging benchmark. It's so different. In the COCO image, you have, I don't know, apples, ships, sea, etc. It's so different. But we can also observe very little improvement though on the COCO again. So we assume it's because on the ScanNet on COCO they have some indoor data, and we leverage some multi-view information from ScanNet, and at least on those data, in the indoor data, in the COCO, it brings some improvement. Overall, it brings some very small improvement. Therefore, that's really interesting that you can how you can leverage the multi-view or 3D priors for the 2D downstream task. Yeah, that's basically. Sorry, my phone. Yeah, that's basically the whole work pipeline of this paper. And we also release our code and some pre-trained model. If you want to play around, you can go to this GitHub to play around. And we also release all the logs, etc. You can check out if you want. Yeah. So basically, to answer the question in the beginning, can 3D priors help 2D learning? We think is yes. So if we can somehow get the good loss for the for example the multi-view or geometry, whatever, it will help. And also we think it's not the end. There will be more directions in this way. You can explore more as the thing like the 3D prior to help 2D task. Yeah, that's it. Thank you.
Yeah, I also had this 3D. I'm not muted. I also had this 3D pre-training idea, more or less, and I did it with molecules actually, like a year ago, where you have a 2D representation and a 3D representation of a molecule, and often the 3D is less. Yeah, you don't have the 3D information available, but if you tell the network more or less to reason about 3D geometry from the 2D inputs, then you can already get a bit better representations and a bit better downstream predictions. Yeah, but anyway, thanks a lot for your great presentation and for the information. Yeah, I enjoyed this paper, especially because I also did something similar at some point. But do you think there's like I mean, there's a lot more 2D only data, right? Where you do not have the correspondence between 2D and 3D. And now if I pre-train with some, I don't know, typical augmentations that we use for images a lot. And I have my SimClear or whatever setup, whatever SSL setup you prefer. Yeah, with all of those images, do you think this is just a much better pre-training than we could ever get to with this 3D pre-training?
Yeah, so I also think there's a problem a lot because for the 3D, the current biggest problem is about data. So it's way less data than the 2D domain. So there are two things I'm thinking. One thing is they're actually orthogonal. So you can leverage whatever 2D loss you want and add a 3D as a plus. So basically, I still believe that the 3D information are 2D and the 2D information, they're kind of like, they can be add on each other. And
sure. But how do you do, like, do you pre-train do you first do your SimClear pre-training with a billion images, and then you fine-tune with the 3D pre-training, and then you fine-tune on the actual task that you're interested in? Or
yeah, so basically, for example, if you are domain specific, for example, if I only care about the scene understanding in ScanNet, then I fine-tune, I pre-train again with the depth prior or whatever in ScanNet. I think it will have again, the biggest again will come from here because it's kind of in-domain transfer. Again, for a more generalized information, for example, I want to do whatever I want. It's like open world, right? I don't limit anything. One thing I really think is interesting is, because you don't have depth for every image, but imagine you can download a lot of video from YouTube. If there's no commercial use, you just download it for research. You download a lot of videos and you run a COMAP, and you can get a camera pose. Although it's not accurate, you can still get some camera pose, and some sparse depth. It's basically like the mega depth. I'm not sure, but I think if you pre-training this way, use the multi-view information that you get from COMAP, for example, on the same scale, let's say the data as the 2D data, I think you can still improve upon the 2D pre-trained models this way. Also, another thing I'm thinking is how do you do that? Currently, we use the ImageNet pre-trained model as initialization of our second time pre-training. It's because we have this ImageNet pre-trained model at hand. We just initialize in the PyTorch. It's just one line of code. But if you want to spend more effort, I think if you can jointly training, for example, Moco, on, for example, the download image from YouTube, plus what I said, those multi-view pre-training that you get from the COMAP together, you have these two laws together. If do it properly, I think it could be better if you only do Moco on those images. That's what I think, because you embed additional information from multi-view geometry, etc. That's what I believe. It just yeah. I mean, it just very, it's very difficult in a way how you get this data. It's only about data now. I still believe the data is the core of everything now. Basically, if you have data, then everything will be easier.
Yeah, I mean, that definitely makes sense to me as well. So yeah, any other questions from the audience? Feel free to unmute or something like that. Otherwise, do you want to leave us with any last words?
Yeah. So basically, myself, I'm super interested in how can you leverage the priors rather than only RGB for better representation learning, or even the language now, because the clip is super popular. It's kind of another direction orthogonal to this 3D priors, etc. If I still hope that the people can look at into more this cross-modality learning. Like you can get the 3D priors, you can get the multi-view geometry, you can get the language altogether. I still believe if we have collect enough data and do pre-training like this, we can have the most powerful backbone than ever. I just believe so. Okay.
Yeah, I think here in the reading group we're all interested in mainly building prior geometric knowledge into some networks, and yeah, this pre-training ways is one way. Yeah, I really like this idea of 3D pre-training, and as G said, there are many other avenues of this pre-training approaches to explore. So maybe you can do that as well, and you can also explore the future reading group sessions with all of the information down in the description. See you around.